Okay, so we are moving on from ionic bonds and ionic compounds to covalent bonds and covalent compounds. So a covalent bond are bonds that happen between non-metallic elements, and they are bonds in which the elements are sharing electrons. Okay, so our ionic bonds were between metals and nonmetals. We're going to find covalent bonds being formed between non-metallic elements only. Okay, and it's going to be a sharing of electrons, whereas ionic bonds, one element, the metal, gave away electrons, and the non-metal accepted them. Covalent bonds are when these atoms are sharing electrons, and they do this for the same reason that ionic bonds form, is because these atoms want to be stable. They want to fulfill that octet rule, but they can do it through sharing rather than just gaining or losing electrons. Okay? So the term we use for a covalent compound is molecule. Okay, so if it's a compound, so one or more or two or more different elements um, bound together covalently, we call it a molecule. Okay, so water would be an example of a molecule over here. We've got two hydrogens and an oxygen. Those are all nonmetals. These are covalent bonds that we see here that are holding these things together. So we call it a molecule. Okay. So these covalent bonds can be single, double, or triple. Single bonds, you share two electrons. So two electrons are shared in a single bond. Double bond, you get four electrons. Triple bond, I bet you can guess it, six electrons. Okay. So each bond shares two electrons. If you have a double bond, that makes four. A triple bond, 3 times 2 is 6 electrons shared. Okay. Now let's look at an example of a single bond, okay, which is two shared electrons. Now we're going to use um, Lewis dot structures again. Okay. So let's look at hydrogen, H2, hydrogen bound to itself. So it's the same element. It's a nonmetal. So these are nonmetals binding to each other. We draw the Lewis dot structure for each. Now remember, this hydrogen to be stable wants two valence electrons. But with covalent bonds, instead of like grabbing an electron from another atom, it's just going to share. It's much more egalitarian. So these hydrogens share these two electrons. Each of them can count these two electrons in their valence shell. So both of these electrons are now stable because this hydrogen has two, this hydrogen has two. Okay. And then we can represent this covalent bond with a single line like that. This represents one covalent bond, a single bond. So when you see this line in a Lewis structure, that's representing two electrons that are shared in a covalent bond. Okay. So let's look at water, another classic example here. Okay, so these are all nonmetals that are binding, two hydrogens and an oxygen. Draw the Lewis structures. Okay, so again, these hydrogens want two electrons for their valence shell. Oxygen wants 8, so oxygen needs to gain two electrons in its valence shell somehow or another, but it's not going to do it by grabbing them like we've seen before. It's going to share them with hydrogen. Okay, boom. So each of these hydrogens can count both of these electrons, right? So this hydrogen has these two that are circled, this hydrogen has these two, and if you count all the ones that the oxygen has, we've got the 6 original, and then it also counts these ones it's sharing with hydrogen. So there's 1, 2, 3, 4, 5, 6, 7, 8 around the oxygen. So that fulfills that octet rule. It's happy. And we can draw the complete structure there, and we represent those covalent bonds with lines. And then oxygen still has these pairs, these lone pairs of electrons here, okay, that are unbonded. And this is why, if you see this shape to water, it's kind of this bent shape, it's because of those electron pairs. If you get into chemistry, we'll talk a little bit more about that and what makes water so special, because it is super, super special. It's the only way we know. It's the reason life is possible, is because this molecule is so special. Um, and it's also an example of single bonds. Okay, so let's look at an example of double bonds. So this is where two pairs are shared. So when oxygen binds to itself, it makes a double bond. And we have O2. So we draw our two Lewis dot structures. And again, these are covalent bonds. There's no metal. So there's no metal to give these oxygens electrons. So they've got to share. They've got to play nice. All right, so they can share this pair. And this is why when you draw these Lewis dot structures, you don't pair them up unless you have to. Because when they're not paired, these electrons are available for covalent bonding. Okay, so they can share these two. Okay, but that still doesn't make them happy. If we count up the electrons in this oxygen, we got 1, 2, 3, 4, 5, 6, 7. Not happy. So we got to share that other pair too. And then we can count them up. 1, 2, 3, 4, 5, 6, 7, 8. Cool. Oxygen's happy then. And to draw this structure, we represent the double bond with two lines. So each one of these lines represents two shared electrons. So there's 4 electrons in this double bond. One more example. We've got CO2, carbon and 2 oxygens. We draw the Lewis dot structures. Okay, we've got 2 oxygens. So we can form 2 covalent bonds with each of these oxygens, the carbon can. And this is also what makes carbon so special, right? Because it's got 4 electrons available for covalent bonding. So it can make lots of bonds. Okay, so we've got a double bond between the carbon and each of these oxygens. And we write this one like this. Okay, so CO2, this is carbon dioxide. Okay, so example of triple bonds. Triple bonds are when 6 electrons are shared. Okay, these don't happen super often. They're not as common as double and single bonds. They're also very, very strong. So when nitrogen binds to itself, it will make a triple bond. Boom, boom. Takes 3 covalent bonds to fulfill the octet rule for each of these nitrogens. So now if we count it up for this nitrogen, we can count 1, 2, 3, 4, 5. Then it gets the shared ones, 6, 7, 8. Okay, so each of the nitrogens is now happy. And we write this one, you probably guessed it. Triple bond you represent with 3 lines. So when you see each of these lines, it's 2 electrons. All right, over here, this is liquid nitrogen here. Next year in biology, you'll talk a little bit about the nitrogen cycle and why it's so important. Nitrogen is really, really important for life, for building proteins specifically, and DNA. But this triple bond is really hard to break. And this is the form that nitrogen is in our atmosphere, this N2. We can't just break that bond. We don't have the physiology to do it. So we have to get our nitrogen from eating other organisms. There's bacteria that can break these triple bond, this really strong triple bond. So we have to use them to get our nitrogen. We can't just breathe in the nitrogen that we need, even though nitrogen is the most abundant element in our atmosphere. It's the most abundant gas. Most of what you're breathing in is nitrogen, but we can't use it because of this ridiculously strong triple bond. It's tough to break. All right, so there is covalent bonds. The big difference between covalent bonds and ionic bonds is that covalent is sharing electrons. And with each of these shared pairs, both of the atoms can count that shared electron, both of the shared electrons in their energy shells to make that octet rule, to fill those up, to make them stable, to make them happy. All right, so you still need to know how to draw these Lewis dot structures. They're super handy when it comes to this. They represent the bonds with lines like that, each one representing 2 shared electrons. All right, you got some practice with it.